So let's go ahead and take a look at the math associated with this by first examining some typical kinds of KSPs. I've got two different kinds of salts I want to show you. One of them I'm going to call a soluble salt. And the other one I'm going to tell you is called a sparingly soluble salt. Let's look at their K values and what we're talking about. When I say that a salt is soluble, I'm saying that it is going to dissociate completely in water. Sodium chloride, sodium hydroxide, they dissociate because sodium ion is soluble completely to make sodium ions and chlorides. I started out with this. I made all of that. The ratio of this, the sodium times the chloride over this, would have to be equal to infinity. Same thing down here. Because I've taken this and dumped it in the water and made only this and none of that, the KSP is infinity. Now we know that this is ridiculous. The way we know this is ridiculous is, first of all, mathematically, I can't create a situation where every bit of this dissolves like this and I have none of this left. I mean, very practically, this would be the same as saying, I've got a thimble of water. I'm going to continue to pour sodium chloride in it forever and ever and ever, and every darn bit of the sodium chloride will dissociate. Well, that's not what happens. When you go out to the ocean and you stand in the ocean and you take a sip of water in the ocean and it's pretty darn salty, it's not infinitely salty. There is going to be a maximum capacity of the sodium chloride to go into solution and make sodium ions and chloride ions. What is that actual value that we get? Is it infinity or not? The answer is it's not infinity. It's a number far less. But it's a pretty darn big number. And rather than deal with the complications of that big number, in a freshman chemistry course, we ignore entirely the notion that that KSP is some value that's large, and simply say, let's just say everything dissociated. If I started with 0.1 molar sodium chloride, it made 0.1 molar sodium ions. And ignore the fact that there's still some of this. If I start with 0.05 molar sodium hydroxide, then that's 0.05 and that's 0.05, and I ignore the fact that there's still some of this. That makes the calculations we're going to do moving forward enormously simpler to deal with. So in general, I'm going to be telling you about these things called soluble salts, and we will be making the assumption that they dissociate completely and go from there in terms of working our problems. Now, some of you might be annoyed by what I've just talked about and say, no, I want to know more. I want to know what the actual KSP of salt is. Well, the neat thing about this is you can go home and find the KSP of sodium chloride in the privacy of your own home doing the following. Why don't you go home and, just for kicks, get yourself a beaker and put some water in it. I don't know, put 100 milliliters of water in it. And then I want you to dump in a bunch of salt. Dump in as much as you'd like. Now the salt's going to sit on the bottom. That's all my salt sitting down there. Some of that salt is going to dissociate up into solution to make Na plus and Cl minus. But after a while, I'm going to get to equilibrium, where the amount of salt sitting on the ground and the amount of sodium ion and chloride ion up in solution are going to be at equilibrium, and I can't get any more of this into solution. I have a saturated solution of sodium chloride. That's the term for it. Saturated solution at equilibrium. The maximum amount that can go in there. That maximum amount is not infinite, so my KSP isn't infinite. It's some number less than that. Well, what is that number? Well, I can find out that number because if KSP is equal to sodium ion times chloride ion, then if I can figure out what these saturated solution amounts are, I can multiply them together, and that's going to tell me my KSP. So is it possible for me to find out what that saturated salt solution is? Sure. Why don't I take that saturated salt solution and pour carefully the liquid saturated solution off into another container. So now I have a container which is just saturated Na plus and Cl minus. I've left behind the stuff that was sitting on the bottom. Now you know what I'm going to do? I am going to evaporate all of the water away. Once I evaporate all of the water away, what do I have left? A bunch of sodium chloride crust sitting all around inside this container. That sodium chloride crust is what used to be dissolved in water. If I weigh it, and I have its amount, then I now have the grams of NaCl. I divide it by 58, and I have the moles of NaCl. And then I divide that by my original volume that I poured into here. Well, that's a molarity of the solution that was saturated. I take the molarity of that solution, I multiply those two numbers together, and I end up with the Ksp. You can do this at home. Students do this for extra credit for me sometimes. The answer is, and it's a difficult problem to do at home, but the answer is that the K value is going to be on the order of around 5 to 10. Not infinity, but still a pretty healthy number. A number that comes because sodium ions a couple molar, chloride ions a couple molar, 2 times 2 is 4, or 3 times 3 is 9. That's where this comes from. The maximum concentration of sodium ions, the maximum concentration of chloride ions in solution, have to be equal to each other from stoichiometry, is equal and around 2 to 3 molar. That water that you drink in the ocean that's pretty salty is no longer pretty salty. It's 2 or 3 molar salty. And the Ksp associated with it is around 5 to 10.